Welcome, everyone. My name is Ricardo Camacho, Director of Software Safety and Security Compliance. Thank you for joining us today for this presentation, MISRA C 2025, Everything You Need to Know. We've got a great session lined up, educational, informative, and practical. We'll cover key updates in MISRA C 2025 and show you how to perform static analysis using Parasoft C++ tests with the new standard. Our presenter today is Michal Rozenau, project lead at Parasoft and an active member of the MISRA C and MISRA C++ working groups. Michal brings deep expertise in safety-related applications and helps organizations meet compliance with standards like IEC 61508, ISO 26262, DO 178C, and EN 50716 or EN 50128 for rail. He also leads the development of the static analysis engine in Parasoft's testing solution. So you're in excellent hands. And beyond that, Michal is a great person and a wonderful friend. Say hello, Michal.
Hello, everyone.
All right, let's take a look at the agenda. So first, I'll set the stage with a quick overview of static analysis, the cost of defects when shifting left. Now, also how Parasoft static analysis integrates into your development workflow and how AI is being used in this space. Then Michal, our expert, will guide you into what you need to know about MISRA C 2025, the what's new, and the two new Addenda documents. He'll walk you through the key additions and changes and provide some comparisons to MISRA C 2023. You're actually going to love it. After that, Michal will give us a live demo of MISRA C 2025 in action using Parasoft C++ test. I'll then wrap it up with a few call to actions and we'll move right into the Q&A session. All right, let's get started. Now, to put things into perspective, static analysis is primarily a method of debugging and identifying implementation issues by examining the source code without executing the program. This is done early in the development lifecycle during the implementation phase. You may have heard of the term shift left. Static analysis is a perfect example of shifting software testing to the left. You may wonder why this is important. Well, because developers can catch and fix issues before they become more complex and expensive to resolve later in the development cycle. It's a well-known fact that fixing bugs early is significantly cheaper than dealing with them post-deployment. I'll go into more depth in this on the next slide. But beyond defect detection, static analysis helps maintain high coding standards, which is crucial for safety and security critical embedded systems. And I'm talking about software in medical devices like heart pacemakers and infusion pumps, avionics systems that actually keep aircraft flying, or automotive systems used in autonomous vehicles and ADAS systems. To support this, we have industry safety coding standards like MISRA, and there are others like AUTOSAR C++ 14. However, not all static analysis tools out there fully support these standards. Parasoft static analysis does. Now, the same goes for security coding standards like CERT, CWE, OWASP, and more. We support them too. Another key point, static analysis is automated, repeatable, and can be run frequently. You don't need to create test cases to uncover issues like you do with unit integration or system testing. Static analysis also provides insight into code quality metrics like complexity, readability, testability, and maintainability. And as a byproduct, it actually helps educate developers, encouraging better coding practices and making them better software engineers overall. Now, I want to come back to the shift left concept, which is one of the most powerful approaches in modern software development for early error detection. Traditionally, testing and debugging happened late in the development cycle after coding integration, even initial testing. This often led to critical bugs being discovered when they were much more expensive and time-consuming to fix. By applying static analysis during implementation, developers are alerted to issues immediately and can resolve them right on the spot. This results in higher code quality from the start and a substantial reduction in downstream defects. The chart on this slide illustrates the cost impact based on actually a real study. So for example, fixing a moderately complex defect during implementation might cost around $88, but if found during QA or in the field, the cost rises dramatically due to the added effort, coordination, and potential customer impact that it takes effect. Now, when a defect reaches the field, it's actually the most expensive, requiring patches, possible recalls, reputational damage, and actually you have to do a lot of retesting. Now, despite this, I still come across teams that don't use static analysis. If you're not already using it, I highly recommend adopting it. And if you rely on suppliers for software components, make sure that they follow coding standards like MISRA or Cert for Security. This promotes consistency, safety, and security across your supply chain. Now, these standards are developed by experts with years of experience, just like Michal, who actively again contributes to the MISRA C and C++ working group. So take advantage of his deep expertise and also Parasoft's robust static analysis solution. Now, in case you're not aware, I wanted to quickly highlight how Parasoft leverages generative AI to accelerate fixing code violations. This is actually a true game changer. We've integrated GitHub Copilot into our C, C++ test VS Code extension. But what sets Parasoft apart is how we actually guide the AI to produce high quality compliant code. The key lies in two things here. The rule documentation, we embed detailed guidance so the AI understands the intent behind each rule. And the second one is the chain of thought reasoning. So this prompts the AI to solve problems step by step, leading to more accurate and complete fixes. So the results you're going to get are improved accuracy, fewer false positives, and more reliable fixes, stronger compliance. Fixes are aligned with standards like MISRA, CERT, and others, whichever ones you're using. Now, they're also going to have better handling of complexity, even in safety critical large-scale code bases. Now, all of this leads to higher quality code, faster timelines, and fewer costly issues downstream. So by choosing Parasoft, you're not just using a tool, you're empowering your team to build high quality compliance software with confidence. Now, the QR code that you see will take you to a recording of our static analysis AI-driven code remediation capabilities. It's really cool, so recommend it. Now, okay, you know what? Let's get to the exciting stuff. Michal, I'm passing it over to you.
Thank you, Ricardo. So now let's talk about MISRA C, which is definitely the most popular set of coding guidelines for developing safety critical applications. It is widely adopted in all the verticals, starting from the automotive, going through railway, aerospace, defense, medical, and industrial automation. So whenever functional safety regulations are in place, but it is also used to ensure the general quality of the developed C code. Within the recent publication of MISRA C 2025, organizations may wonder what it means to them. Is this a new standard with a new set of guidelines, or just a continuation? And what it takes to implement the MISRA compliance process in their project. That's why in this webinar, we will try to describe what is MISRA C 2025, how is it related to the previous revisions of the guidelines, are there any new guidelines introduced by this new document, and what are the changes to the existing ones. We will check what MISRA says about AI-generated code and what other documents have been recently published by the MISRA C working group. And at the end of the session, we will quickly go through a demonstration of how static analysis tools can help enforce MISRA guidelines. Let's start with the quick history of the MISRA C guidelines. The first edition has been published back in 1998, so 27 years ago. Based on the feedback and following the evolution of the C language itself, the new editions of the MISRA C guidelines were published in 2004 and 2012. The latter has been augmented with technical corrigendum and amendment, followed by the publication of consolidated MISRA C 2012 revision 1 document in 2019. Further technical corrigendum and amendment documents were published, and then we got the next consolidated document, MISRA C 2023, described also as the second revision of the MISRA C 2012. For the last 2 years, MISRA C working group has been working to provide the most up-to-date coding guidelines for using C in safety critical systems, and the result of this work has been recently published as MISRA C 2025, which is available now in hard copy and as a PDF document from the MISRA web store. So as we can see, MISRA C 2025 is not a completely new set of coding guidelines, but an incremental update to MISRA C 2023. The new document has been announced very recently in March. So what has changed in MISRA C 2025? There are 4 new rules introduced in this version. 2 rules were removed, which means they disappeared from the document as separate guidelines, but the enforcement of appropriate practices remains through other guidelines. 1 rule has been disapplied. We will discuss that in details in a moment. 3 rules have been renumbered, which means they have been moved in the document to more appropriate sections. And 13 other rules have been modified. This gives us the total number of 224 guidelines in the new MISRA C document. MISRA C 2025 gives us some new restrictions, disallowing some code as potentially dangerous or causing developer confusion. This includes use of tentative definitions in headers and external declarations in source files. There is a new rule that disallows implicit comparison of pointers to null. This has been previously handled by multiple rules, but not all cases were covered. So now we have a specialized rule for this. There is a new rule that covers use of non-active union members. And the one of the existing directives has been updated to ensure use of unique include guard macro identifiers in a project. Finally, conversion between pointer to object and integer now requires explicit deviation procedure, as Rule 11.4, previously only advisory, became now required in MISRA C 2025. So let's go through some of these in more details. First, there is a new rule: a union member shall not be read unless it has been previously set. When a union member is written and then a different member is read, we generally get implementation-defined behavior. And if the member that is read is wider than the one that has been written to, the read value is unspecified, or in case of C90, it is an undefined behavior. The new rule has an exception for reading from the member being the character array member, as aliasing reads through character types is guaranteed by the standard to result in the valid byte access read. Next, the old MISRA C 2023 contains rule 11.3, which forbids conversions between a pointer to an object type and a pointer to a different object type, as it may result in the pointer that is incorrectly aligned or in accessing an object through a pointer to incompatible type, both of which result in undefined behavior. So that's why the rule has required category. But converting through an integer type has been guarded only with the advisory rule 11.4. So this construction, even though at least as bad as the previous one, did not require formal deviation procedure. Now in MISRA C 2025, the first construction is still prevented with the same rule 11.3. But the second one results now in two violations of a required rule, as the category of rule 11.4 has been amended to required. At the same time, the rule has been modified to include an exception case, but we will get back to it in a moment. MISRA C 2025 updated also the directive that requires using some mechanism to prevent a header file from being included more than once. This is usually achieved with using macro guards in the headers. Now, if we have another header file in the project which uses the same macro identifier as the include guard, this may become a problem if both files are included into one translation unit, as the contents of only one of those files will be in fact included. The rule definition used in MISRA C 2023 made it not clear whether such situation is compliant or not, while the new version of the guideline makes it perfectly clear that the identifier used as the include guard macro needs to be unique across the project. Okay, so these were some of the new constraints posed by the MISRA C 2025, but the changes done in the new version of the guidelines introduce also multiple additional permissions. There is no requirement to use with specific type defs for floating point types anymore, as the number of bytes is actually just one of the attributes of the floating point type implementation. The guidelines allow now conversions between pointers and int.ptrt or uint.ptrt types. They allow immediate conversion of newly allocated memory to a specific pointer type, of course remembering that the use of the dynamic memory is still discouraged in general. Rules on switch statements have been updated to allow terminating switch clauses with statements other than break. Macro arguments constituting expressions can now be delimited using delimiters other than just parentheses, so no need to put parentheses everywhere anymore. And finally, the rule that disallowed multiple return statements in a function is now disapplied by default. Let's start with the last one. In MISRA C 2023 and earlier versions of the guidelines, this code was non-compliant with the advisory rule that says a function should have a single point of exit at the end. This rule has been controversial for a long time now. When someone asked why this rule exists, the usual answer was because it is required by the functional safety standards like ISO 26262 or IEC 61508, with their single entry, single exit principle being a part of the general modular programming approach. The thing is After doing deeper research, it turned out that the requirement originates from the unstructured languages like assembly, which allowed jumps between arbitrary points in the programs. Structured languages like C or C++, with their concept of functions, do not violate this principle by the definition of the language, as each return from the function always returns to the caller. That brought up the idea of dropping the rule from the MISRA C guidelines completely. Yet, there were voices against that, as it turned out that some organizations still would like to be able to enforce this rule as a part of their MISRA compliance process. That's why the rule remained in the MISRA C 2025 document, but as a disapplied rule, which means that the enforcement is not required unless a project decides otherwise through the guideline recategorization plan. Another item with loosened restrictions is Rule 11.4. We already discussed it in the context of changing its category from advisory to required, and then we mentioned that an exception has been added to it. Here we see two cases which are non-compliant with MISRA C 2023, as we are converting a pointer to the integer type. MISRA C 2025, however, introduces an exception that allows conversions between a pointer and int ptrt or uint ptrt types, as such conversion is allowed by the standard. Similar situation we have with Rule 11.5, which restricts conversions from a void pointer to a pointer to object type. Here also an exception has been added to allow conversion, allowed by the standard, where a pointer to newly allocated memory is converted to a pointer to an object type. Please note that in order to keep the rule decidable, MISRA allows only immediate conversion to be made. And the last rule we will discuss today is a rule that in MISRA C 2023 required each switch clause to be terminated with a break statement, where the rationale points to the fact that lack of the explicit break statement leads to the potentially unintentional fall through to the next clause or of the end of the switch statement. While this is generally true and the non-compliance of case 3 and default clauses is not controversial, it is different for case 2, where calling abort ensures the control flow will not continue in this function, and in case 4, where explicit return statement makes it clear that none of the following statements in this function will get executed. And actually adding additional break statements just to make this rule happy will obviously introduce an unreachable code. Therefore, MISRA C 2025 changed the rule to allow other statements to be used to terminate switch clauses. This includes calling non-returning functions like abort or using any jump statements, so either break, continue, go to, or return statement. So as you can see, the new update of the MISRA C guidelines focuses on making life easier for the developers, at least as much as on restricting use of additional cases of dangerous C code. Of course, only in these cases where the overall quality and safety of the code is not compromised. Now let's talk about automatically generated code, including code generated using LLMs. MISRA guidelines treat automatically generated code specially. There is a publicly available base guideline recategorization plan available for the automatically generated code, where several advisory guidelines have their category reduced to disapplied, and for some other required guidelines, MISRA permits are provided. which can be used as a base for deviating the rules in the auto-generated code. This is mostly on the grounds that such a code is not intended to be read by the humans and that the automatic code generators, let's say it, they know what they are doing. That's why, not wanting to stay quiet on the recently growing amount of AI-generated code, MISRA decided to explicitly state that the automatically generated code refers to the C code that is emitted by a qualifiable code generator that deterministically translates an input program expressed in a high-level modeling language into semantically equivalent C programs, and not the code fragments that are produced by stochastic processes, statistical language models, or machine learning-based approaches. Therefore, code generated by the AI in the context of complying with MISRA guidelines should not be treated the same as the code generated deterministically by the code generators from a model, and such AI-generated code should be treated just as if it has been written by the developers. Now, apart from the MISRA C 2025 document itself, MISRA recently published two new addenda. Addendum documents usually provide mappings between MISRA C and other coding guidelines. So far, the following addenda were released: mapping to MISRA C 2004, mapping to Secure C, mapping to Cert C, and to the Language Vulnerabilities ISO standard. Now, newly published Addendum 5 provides mapping of the MISRA guidelines to CWE weaknesses, focusing on memory safety issues, specifically on those CWEs that are children of CWE 1399, memory safety category, or CWE 119, improper restriction of operations within the bounds of a memory buffer class. 42 of such CWEs applicable to C language have been identified, and for each of them some kind of mapping to MISRA C guidelines was found. Addendum 6 document has been produced to assess the applicability of the MISRA C guidelines to the Rust programming language. And hopefully this document can become a basis of future work within MISRA in collaboration with the wider Rust community. Within the addendum, each MISRA C guideline has been assessed whether the problem it mitigates can appear in the Rust program, both for Rust in general and for the safe Rust, excluding use of unsafe and external features. Note that the document is not the actual set of guidelines for Rust, but should be rather treated as an initial list of potential problems that shall be somehow mitigated. Further deeper analysis on how to enforce safety in these areas is still required, whether to be done by the MISRA, by the Safety Critical Rust Consortium, or as a joint work between those two. So that concludes the walkthrough of the recent publications produced by the MISRA C working group. So here I have a very simple project hosted on GitHub and developed locally in the Visual Studio Code. Both within the local VS Code and GitHub, Parasoft C++ test will be used to check compliance with the MISRA C 2025 guidelines. On the desktop, I am using C++ test integrated into my VS Code to check the code against a subset of rules for performance reasons, and the GitHub actions will ensure that complete check is performed using C++ test when the pull request is created. So first thing I'm going to do is I'm going to create a new branch I will be working on, and I'm implementing main loop function together with the helper function. Now I will use C++ test to execute the analysis of the modified code. When the analysis is done, I can see the problems reported directly in my IDE. Here we can see 4 violations of the MISRA rule 11.11, which say that the value of a pointer is used as a controlling expression of the if statement and as an argument to the negation operator. All of those are reported in one function. With C++ test, we can leverage generative AI capabilities to provide detailed information about the reported violation and to suggest a fix for it. C++ test provides AI with the appropriate context, including rule documentation details, and uses chain of thought reasoning to achieve the best possible recommendations. I chose explain violation for one of those violations, and now I can review the information provided by the GenAI together with the proposed fix. Of course, all AI-generated recommendations should not be taken for granted, but should be manually reviewed for completeness and accuracy. I can now apply those proposed changes into the editor and review whether I agree with them. Alright, so please note that in this case, AI provided proposal to fix all 4 of the reported violations at once. All these changes look good to me, so I choose to keep them, and now I can rerun the analysis to see if the problems are really gone. We can see that no problems are reported anymore, so I am ready to push the changes to the server. But before I will do it, I will also review the report generated by the Parasoft C++ test during the analysis. We can see that indeed no problems are reported, but there is one suppressed violation. It is a violation of rule MISRA C 2025, rule 20.15, which is one of those rules that have been recently renumbered. And in the suppression reason message, we can see that this suppression has been automatically applied by the tool based on the existing suppression of equivalent rule 21.1 from MISRA C 2012. And if we take a look at the message.h file, we can see that this is the rule that has been previously suppressed. This optional C++ test auto-suppression mechanism, based on the existing suppressions of equivalent rules, makes the process of migrating between the 2 versions of the coding guidelines much easier. Alright, so now we are ready to push our changes to the server and create a pull request on GitHub. This will trigger complete MISRA compliance analysis to be performed on the server. We can see the status of our pull request directly on GitHub. And when the analysis is finished, we can see that the complete server run found one more issue that has not been spotted in the local run. It says that an inactive field, union member field I, is red, while the field that was written to was F. Let's review the actual execution path that causes this problem. And indeed, we can see that inside create float message function, we set the value of F, but the message kind is incorrectly set to int32 instead of float. This looks like a simple fix which we could do directly on GitHub, but let's go back to the VS Code for now. Where we can also import the results from the GitHub run into our IDE. So now we can go to the place which contains the problem, make a fix, and push it back to the server. Now, if we go back to the pull request on GitHub, we can see that the scan has been re-executed automatically. And when the analysis is done, we can drill into the details and we can see that all the checks, including MISRA compliance check, has now passed. So our pull request is ready to be merged into the master branch. All right, so that concludes our demo for today. So now back to you, Ricardo.
Thank you, Michal, for the excellent overview of MISRA C 2025 and that very impressive live demonstration. It was very educational, and I'm sure for all our folks out there. Now, if you guys would like an in-depth demo, please scan the QR code you see on the left side of the slide. And to download the C++ test extension for VS Code, which uses AI to help remediate static analysis violations, you can use the QR code in the center. And if you're interested in learning more about Parasoft products and solutions or exploring our extensive library of content, scan the QR code on the right. If you have any questions after the webinar, feel free to email us at info@parasoft.com. And you can also follow us on X, Facebook, and YouTube. All right, let's go ahead and open it up for Q&A. Just got a few questions here. Let's see. First question, how does Parasoft static analysis differentiate itself when handling false positives compared to other tools in the market? Okay, that's a great question. One of the biggest challenges in static analysis adoption is developer fatigue from false positives. And that's something we've taken very serious at Parasoft. Now, our static analysis engine is powered by over 35 years of expertise, and we use advanced control flow and data flow analysis to significantly reduce false positives right out of the box. But more importantly, we give teams the ability to tune and customize the rules to fit their code base and whatever the project needs are. So you're not locked into a one-size-fits-all kind of approach. Also, our rule documentation includes context, code examples, and remediation guidance, which not only helps developers quickly understand issues, but also improves the trust in the results that it provides. And now with the AI-assisted remediation, you're going a step further by proposing fixes that are aligned with developers' intent, making it easier to validate and accept those changes, as Michal showed you in his demo, which is really, really impressive. Okay, let's see. We have another question here. This one looks like it's for me. How do the new guidelines cover at least some aspect of the C23 language?
All right, so I will answer no. So this MISRA C 2025, just like the previous 2023 edition, it covers C standards from C90 through C17. And the new version of the language, so C23, also known as C24, it was published October last year, so it is not yet included in the new MISRA document, but the working group has it on the radar, and for sure we will see some MISRA guidelines for this new version of C at some point.
Mm-hmm. Okay, great. So looks like another question here. How does the integration of generative AI like GitHub Copilot balance automation with the need for safety certification or traceability in regulated industries? Okay, so yeah, that's a very timely question. The key to balancing AI with safety critical requirements lies in control and context. So when we integrate GitHub Copilot into our C++ test VS Code extension, we didn't just plug it in, we actually wrapped it with governance. And what that means is that we guide the AI using rule specific documentation. So rather than letting it guess, we give it the why behind each coding rule, whether that's from MISRA, CERT, or whatever standard you're using. And this ensures that the generated fixes are meaningful and actually also lead to compliant code, as Michal showed you there when he reran the code changes. Now, second, we apply chain of thought reasoning. The AI doesn't just suggest a fix, it explains the logic behind the fix, step by step, as we actually saw. And this is crucial for traceability as it creates an auditable trail that aligns with functional safety standards like DO 178C and ISO 26262. So instead of replacing human judgment, our approach enhances it with automation that's explainable, audible, and ultimately certifiable when paired with your existing development process. We got another question here. In the past, MISRA published amendment documents that describe the changes in the tool. Do we have it for the MISRA C 2025? So this must be for you.
Yeah, interesting question. So indeed, in the past, MISRA published a number of amendment documents for MISRA C 2012, and there were definitely pros and cons of such approach. So for sure, it was easy to understand the difference between the two subsequent versions of the MISRA guidelines. That's true. But it was not so easy when given rule was changed in several amendments. So then trying to figure out the actual text of a rule after several such changes was not an easy task. And that's why MISRA C working group now decided to publish new versions of the guidelines as complete standalone documents only. And MISRA C 2023 was the document that incorporated all MISRA C 2012 amendments. And now MISRA C 2025 is the first update published without the amendment. So still, one of the appendixes, it contains a list of changes since 2023. So it should be easy to see which of the rules have changed and which not.
Okay, great. We have another question for you. Not a technical. Oh, sorry. Could you talk about capabilities that your solution offers for dynamic memory allocation in C and C++?
All right. So first of all, since this is a MISRA C webinar, we need to say that using dynamic memory management is at least advised against by the MISRA guidelines, but nevertheless, Parasoft C++ test, it contains a number of static analysis rules related to that topic, starting from rules that will find memory leaks or using bad deallocation functions for C++, so mixing new with free or array delete with regular new. And also we have a number of rules that will report issues related to some buffer overflows, for example.
Okay, great. And it looks like we have one last question. Will this video be available for later use? Yes, these videos are made available on Bright Talk on the Parasoft channel, and I'm sure we'll also be putting it on YouTube. So, so look out for them, and so you can replay them and share them with your colleagues. Michal, thank you very much. That was an excellent presentation and demo. Great. And folks, we have a lot of content and other recordings as well that you might be interested in. So visit the Bright Talk channel or visit our website. Anyways, that concludes the presentation. And take care, folks. Bye-bye.